Yes? I mean that the density is 1 gram per centimeter cubic, 1 gram per centimeter cubic, for example, if you want to think very handy. So and it remains 1 centigram, but this is wrong. This picture is wrong. Just I give you this example, just to make it easier life for you. Anyway, it means that the form of this as a form and the shape, the surface is remain have the same shape after the time. So this is the bond, and with this we call it microcanonical. This pattern called ensemble. So ensemble is a set of the systems with the almost all the same, have the same property, like the energy, like 1 million hydrogen atom, for example. They make 1 million. They make 1 million hydrogen atom, for example, in the one system. They make 3 million dimensional, no, 6 million dimensional phase space. No? Because hydrogen atom has a 3 coordinates, so we have a 1 million. So 3 million coordinate here, 3 million coordinate here. You see the power of statistical physics. So, and you were talking about the 6 million dimensional hydrogen atom, about the general property of that. 6 million hydrogen atom as an ensemble, how they have the pressure, what's their entropy, what's the So this is the power of statistical physics. So microcanonical is that. Is it any other solution for this equation? One solution is rho be constant. So when rho is the constant of everything. There is another very interesting solution, is that the rho be function of the edge. No? When rho is, and this is a color canonical.
So it is also equilibrium?
Yes, of course, you will see. When rho is the function of the edge. First, I want to ask you that, are you agree that when rho is the constant, the stationary condition will be satisfied or no? Huh? Yes. Let me to see partial derivative of some constant things, partial Poisson bracket. Okay. Partial derivative of that is 0 because this is a constant. What is the Poisson bracket of something is constant? You need to show that is partial derivative of that. Because then this is a constant, so constant. There is no any functional form for the rho. So this is the first. Second one. The second is the canonical. But this is not very trivial, huh? That's not very trivial. What is the rho as a function of the edge and the edge? Okay. So what is the first partial derivative of rho h with respect to qi? So you can safely write it that is rho prime h. Rho prime h is d rho dh. We use the magic chain rule actually. Minus, yes.
The first line is the Poisson bracket? dh by dv.
Wait, just.
dh by dv, partial dv.
Yes.
dh.
Yes.
And second term also.
Yes, I
Will be
know.
partial,
I'm doing that.
action.
Yes, I'm doing that. I'm doing that. Okay, let's move. Let's move. So you will do that at the task at home. I don't do that. You will do as a homework. Anyway, we need also, you will ask, I will ask you also to prove that this Liouville theorem is invariant under coordinate transformation or canonical transformation. I mean, if you change the coordinate system from Qi to Qi as a function of the Qi and the Pi nu, and Pi goes to the Pi, Qi and the Pi, so everything will be changed, like the Poisson bracket will be changed. For example, the Poisson bracket rho at the edge with respect to Qi and Pi, I will ask you to check it that what's the relation between this Poisson bracket and if you have a new set of the coordinate called canonical transformation. Anyway, you will show that under the canonical transformation, the Poisson bracket becomes invariant, and when this is invariant, so the form of the Liouville theorem is independent from the coordinate system. So the Liouville theorem holds under any type of canonical transformation in coordinates. So what about the average? So the average of any function now in the phase space, any function of Q, when I write that means that, or Qi means that the Q1, Q2 and the Qa3n and Pi, P1, P2 and P3. The average is given as the integral over the that looks like that. We give the weight to this function at the pointer in the vicinity of this infinitesimal volume. We give the weight for that. So this is the weight for this function. We give the weight to this point, and this is the total. It looks like the. Do you remember any example like that in the classical mechanics? This is exactly center of the mass. Yeah, this is center of mass. Yes, like the density of the mass. volume and the coordinates. Yes? It gives you the center of mass. It gives you the first moment inertia of the system. So it looks like the moment inertia. Exactly. But before, if I don't have the form of the rho, for example, if rho is a constant, so for microcanonical you will get some things. For microcanonical you get the average of any function when the system in the phase space, when the system is in equilibrium and when the system is described by microcanonical approach is given by rho 0 f So what is that? You see, you will have this D3NQ, D3NP. This is, I call it unit volume. This is the minimum volume, minimum quantity you can have in the phase space. It's given at the volume of the one cell. One cell in the phase space have the volume of D3NQ, D3NP. I call it the sigma 0. And the top is just, I don't know what your top is, this integral. You needed to know that what's the, okay. We always talk about the classical, but actually, basically, when you have so many particles and they are obeying the rules of the quantum mechanics, so you needed to think about the Q and the P as the quantum mechanical operator, like the quantum mechanics. I want to talk about a bit about this minimum or unit volume. This is actually the volume of the one bit information in the phase space. 1 bit. All the statistical physics was about the entropy. Entropy was about the information. How much information you can gather. So the minimum of information is the bit. So as far as we know is the bit. And you have a qubit and the other things. So 1 bit information from statistical physics is equivalent to this volume. I want to show that how much is this? The volume corresponding to the 1 bit. Okay, are you sure that this volume is an infinitesimal volume? So I can forget about the integral because the size is, I told you we're talking about 1 bit. So I want to write this delta Q, delta P over 3N. Here you need to go quantum mechanics because you are going to the tiny size, so you need to impose the quantum mechanics. Classical mechanics cannot be used for the 1 bit of information or the system which the size is very, very tiny. So, thanks to the Heisenberg principle, you know that the delta Q, delta P is always h over 2. Yes? Can I write this under h? Because as I told you, then h is 10 power minus 34 And h bar, this is a Dirac, this is the Planck, Planck constant, and this is a Dirac constant. Dirac constant. The order of h bar and the order of the h are almost the same. So I know that if I calculate the volume, it will be something different, but I want to tell you that this is the order of h3. So it's a very tiny number, very tiny number. Just imagine that the n is very big number, Avogadro number. So h is 10 power minus 34, 10 power minus 34 to the power of the Avogadro, so this is a very tiny number. But exists. But this is the difference of the theoretical physics and mathematics. In mathematics, they are talking about the smaller, tiny things and with the size of 0. And we never can have that. You can talk definitely in the phase space if you just be mathematician. You can talk about the point in the phase space with the coordinate 0. So you can say that okay, it should not be any size for the Q and the pair. So the volume is 0. I can say that the volume here, how I can write the volume, I don't know, sigma, okay? Because I use the same here, sigma is 0. But in physics we can't do it because this is the, actually this is the coordinates, and this is the momentum. And we have the uncertainty principle, and we have some advanced name, the uncertainty principle, it works just in the normal quantum mechanics. So if you go to far from the very high field energy, like the early universe, inflation or the quantum gravity or the game of string theory or the game of loose quantum gravity and these things, so you need also to modify the uncertainty principle. So this is called a grand uniform, GUP, generalized uncertainty principle, and something else. So some people working on this business. Anyway, for the physics, we don't have this. In physics, we have the minimum volume, and this is the minimum volume. I didn't say about the integration limit. You didn't see that anything's here. What's the limit of this integration? Where it should we go? So, for microcanonical, we never can fix it the value of the total energy. You understand why? The reason is that you have uncertainty principle in the Q and the P. So you definitely have uncertainty principle for the energy. So for microcanonical, because we are talking mainly about microcanonical, this next lecture and the next lecture also. So I will suppose that the total Hamiltonian of microcanonical ensemble will be bounded between the two values of that. Why I didn't write that between 0 to E? I can write that, but actually by inserting this parameter lambda, I want to emphasize that again you have the uncertainty in the total energy of the system. Some books like Huang and even the Patria, they try to explain this in the page. I think the best interpretation would be that you just accepted the uncertainty principle. We do not need to think about the volume of the surface. The discussion I use it in my formal lectures. But tell me that why I have the permission to get the Hamiltonian constant here. See, this is it shows that the Hamiltonian is actually a number finally, It's between one number and one number. I don't know. 0.9 and 1.1, for example. Why I can take the Hamiltonian constant? Why I didn't write that Hamiltonian between, for example, P squared and Q cubic? I just get it back to my formal lecture. I told you that we are talking about the phase space in equilibrium for conservative systems. For conservative system, always Hamiltonian is equal to the constant. Not actually, at least it's a constant. So I can continue this logic. I can continue and bring the logic inputs. So this is what you need to do. So you will have a system like a classical gas, like the photon gas, like the harmonic oscillator. And we will mention here that the system is in microcanonical ensemble. And you needed to find, for example, the volume, you needed to find the expectation value of some parameters or something like that. So I want to one more mention. This omega actually is